This first graph, the first type of function is when you suspect that you might have something like a quadratic. So if you believe that you have some form of quadratic expression for a relationship or some form of polynomial, then what you can do is you can actually use you can derive values for the power and the a just by analysing data, by converting them. And what we're going to try and do is we're going to convert it into something looking like a y equals mx plus c graph. So if we start off with our function, so this is case 1, which is the polynomial relationship. We begin with y equals ax to the power of b. And if we take the logs of both sides, it doesn't matter if it's ln or lo, we get log of y is equal to log a plus log x to the b, which actually comes out as log base a add on b log base x, a log of x. And this is where we're going to think about it being a line y equals mx plus c, because the b part of this gradient is my m. To plot the points, we're going to plot that as if it's the x. So we're going to plot the log of x against the log of y, and that's my constant part in the middle. So when we plot the graph, we translate all our points. So you've got some data which originally looks like x and y, and it seems to do some of that. When you plot the log of x and the log of y, your points might not be exactly on there. What seems to happen is you get some points which seem to be quite close to a straight line, so you approximate it using your stats1 module into a line y equals mx plus c. The c value tells me the log of the coefficient we're multiplying by, and the gradient tells me directly what the power is. So the gradient, I measure the gradient for this graph, and we've got the change in y, the change in x. So if it's a polynomial form of relationship, if you take the log of the x and log of y and plot them, you should wind up with a straight line. If that is the case, then you do have a graph that is a polynomial. And to get your a, we're going to say log base a is equal to c, so therefore a equals the power of this base. So in this case we're going to do 10. Let's do a little, what should we call it, d. So if we call this the value d, we do d to the power of c, and that will tell me what my a value is, my coefficient in front. The gradient directly tells me what my b value is. So there's some example questions in there that you can use for those. Sorry it's a bit quick, but I'm working from home today and my internet, I've just realised, appears to be getting a little bit shaky. Case 2 is an exponential graph. And what you'll find is you're trying to match a graph y equals a b to the x. And that b value, again, is a number to be worked out. This time, if we do the log of both sides, equals log a plus log x, which of course, come on, which then equates to being log A add on x log b, and this time my gradient is the b part, my intercept is still the log of A, and the x comes straight down from above. So what we've now got is we've got some form of exponential data which goes like that, or if it's a decay it does this, and what you find is when you draw your line of x versus log y, I was just making sure I hadn't made the mistake above, you now get your straight line. And again, you've got approximate points. If it's a decay one, it should go down like that. And what we're going to find out is there's my C, find my gradient, and what I can find from that is again, we're going to use a base D, A equal log, and whatever base D is, A is D to the C, and our gradient part, log base D, and this is a D as well, all the way through, we're using the same base, log base D of B equals M, so B is our base to the power of n, and that will allow us to actually calculate the coefficients for this form of the formula. And so we're using lines of best fit. Okay, hopefully that should allow you to get started with the exercises in the textbook on page 111, 112, 113. Okay.